Okay, so in the last video, we kind of got a rough idea of this mathematical thing called a limit. And we said we're going to look at it from several different perspectives. We looked at it graphically last time and said, well, if the function is continuous, the limit at a given point is just the value of the function at that point. But now we actually said, we finished last time saying, even if the function is discontinuous, clearly from this side and this side, the function is closing in on some value. For the one we actually did last time, I think the value was 2. And we said that while we couldn't algebraically define that yet, in principle, it seems logical to say, for this one, the limit as x approaches 1 of f of x was equal to 2. But now, we understand there's lots of different ways to graph things, and now I can kind of mess around and look at some other graphs. What if I have a graph that looks like this? All of you in 171 potentially, you may not have covered them, but in 171, you may have looked at the greatest integer function. It's a step function. Something that looks like this. And this is a modified step function, but it doesn't matter. So we have a nice little step function like that. And I'm going to arbitrarily say this is x equal to 1 right here, and that value is y equal to -1. Well, now if I do the same thing, suppose I want to find the limit as x approaches -1. I said x equals 1, but I meant -1 because it's to the left of 0. X equals -1. Well, if I do the same thing I said last time, I pick some x's around the one I care about. But now the problem is, if I pick x's to the left of x equals -1, I'm going to get y values all equal to -1. If I pick x values to the right of -1, all my y values are going to be 0. And clearly, in this case, the function is defined here at -1, but it's got a hole right there, and the function's down there, and what do I do as far as my limit's concerned? And now we take my idea of a limit, and we expand it. And we say the limit as x approaches, we'll say -1. From the left, the way we write this, x is from the left over there. They're negative, that's the negative side. So we say x approaches -1, and then we put a little negative sign right there. Now I can say the limit as x approaches -1. On this side, this is the positive side, the right side, we put a little plus right here. And now we have kind of sublimits, extra limits, if you will. We say this, the one that approaches from the negative side, from the left, we call that the left-hand limit. And this one that occurs from the right, the positive side, not surprisingly, we call it the right-hand limit. But now for this function, clearly the left-hand limit, as I approach from the left, the function is always -1. So my left-hand limit for this will equal -1. My right-hand limit, as I approach from the right, all the y values are 0. I put it on the wrong spot, I'm sorry. My left-hand limit was on top. That will be -1. My right-hand limit will be 0. And if nothing else, those are different. And what does that mean? And as far as it goes, as I said, we're going to keep on expanding on our understanding of limits, and we'll kind of keep improving on our definition. But for right now, at least as far as a simple, basic algebraic definition, we can say the limit as x approaches x sub 0 of f of x exists and equals L IFF. If you don't know math shorthand, that stands for if and only if. So the limit as x approaches x sub 0 of a function exists and it equals some number L if and only if the limit as x approaches x sub 0 from the left is equal to the limit as x approaches x sub 0 from the right is equal to L. So essentially, the only way your limit exists is if the left-hand limit and the right-hand limit exist and they're the same value. So in this case, the left-hand limit is -1, the right-hand limit is 0. So then we would say the limit as x approaches -1 does not exist for f of x. Because the left-hand limit and the right-hand limit are not the same. Keep in mind, though, again, we tend to parse things a lot in math. Sometimes you are told to find the left-hand limit or the right-hand limit, and those can exist. Here they clearly do. But then other times you're told to just find the limit of the function. Like we said, there's different ways to define it, and we'll see different ways to prove it and find this limit. One of the ways you can test it is to look at the left-hand limit and the right-hand limit. So, suppose we have this. Draw a nice function. Let's see. We'll go with okay, something like that. That's clearly a function. All of you remember your 171. The only potential vertical line test problems are right there. There's a hole right there, so it doesn't really matter. So that clearly defines a function. And I'll say this is x equal to 1. This is x equal to 3. And then we'll say this is y equals to 1. Y equals 3. And right here, we'll say y equals 6. So then suppose I want to find the limit as x approaches 1 of f of x, the limit as x approaches 3 of f of x from the left, and the limit as x approaches 3 of f of x. Well, then again, I don't have any algebraic tools really to use right now, so we can look at it graphically. The limit as x approaches 1. If I look at x's around 1 and get closer to x equals 1, the y values from the left and from the right clearly both seem to close in on y equals 3. So I don't need continuity at a point. That was our second, more expanded definition of limits. As long as I approach from the left and the right the value 3, then the limit is equal to 3. Find the limit as x approaches 3 from the negative side of f of x. The negative side means the left. So as x approaches 3 from the left, here the function goes up to there. So as I approach 3 from the left, the function approaches 1. So I say the left-hand limit is 1. Now find the limit as x approaches 3 of f of x. As far as it goes, the only real way we have to show that right now is to look at the left-hand limit and the right-hand limit. The left-hand limit is 1. The right-hand limit, as x approaches 3 from the right, the function value comes down and approaches 6, which means the right-hand limit is 6. But now the left-hand limit is 1, the right-hand limit is 6. Those aren't equal. So according to what we just said, this limit does not exist. All things being equal, you should be able to look at a graph and determine the limit of a function at a point by just looking at the graph and looking at the x values and the associated y values. Ultimately, as I kind of keep on saying, we're going to make this more algebraic, but the graphical approach is really useful because if nothing else, when the algebra can sometimes get cumbersome and confusing, this makes it clear what the function does at a point, or even if it's undefined at that point, is irrelevant. I care about the behavior of the function around that point. That dictates what my limit is. Not what the value of the function is, but what the function approaches. And again, it's an incredibly subtle but monumentally important concept in math. The last thing we want to do, we're going to look at another algebraic approach to doing this. We're not going to have time to fully do it in this video, but I'm glad of that because it'll give you some time in between videos to ponder this and think about it. Suppose I have a line. There's a line right there. I care about the rate of change of that line. Can you find the rate of change? I know I didn't put any points there, but you all know rate of change is slope. I can say m is delta y over delta x, y2 minus y1 over x2 minus x1, rise over run, whatever you want to call it. And we all know this slope will be positive. If I gave you a couple of points on the line, plug it in there, get the slope, and be done with it. And what you learn in 171 is, it doesn't matter what 2 points I use, that slope is constant. The rate of change is constant. But now suppose you want to have more fun. Because let's face it, working with lines is good, but that probably gets boring after about 7th or 8th grade when you've worked with lines over and over and over again. So, make it more entertaining. Use our parabola, y equals x squared. Now suppose you have the point 1, 1 right here. Find the slope of that curve at the point 1, 1. What would you do? If I was talking about the slope of a line, I would find 2 points on the line, then just do delta y over delta x and get my slope. So we could try that approach right here. In the next video, I'm actually going to do that with this one and expand on it. But maybe think about it. How could I go about finding the slope at that point right there? What would make sense? And can I somehow use this idea of slope of a line to somehow get the slope, if you will, the rate of change of the curve right there? I'll leave you with that. And like I said, ponder it a little bit in between videos. Go grab a snack, go outside, whatever. Then come back and watch the next video. See what actually happens and if your idea worked.